subscriber to this channel for a while, you probably remember my original video on megastructures, which covered everything from space stations a few hundred feet across to ones encompassing entire stars. Well, we've come a fairly long way since then, and like most initial products, the quality on it is a lot lower than subsequent works, and for me it feels like it needs upgraded. Rather than just redoing the entire video from scratch though, I thought we'd go into each piece in more detail instead. Since these are all about huge things you can build in space or on other worlds, it seemed like the best place to be starting would be on those megastructures designed for getting us off this world to build them in the first place. One of those, the space elevator, is already pretty heavily discussed elsewhere, so we'll touch on it only lightly. Incidentally, you might want to flick on the closed captions if you're having problems understanding me. Ironically, the original megastructures video is the only one on this channel without closed captions since I didn't use a script for it. So when it comes to getting off the Earth and up into space, you really only got two approaches. A self-contained ship, or a structure that can tow you into orbit like a space elevator. One of our big problems about going up into space is just how expensive it is to haul up every single pound of material using chemical rockets. It's the bottleneck, and it means that even if we get stuff like smart robots and 3D printing that can build everything up there from materials lying around, or in situ as it's called, we can never transport people in bulk. And that's our real goal, making space as accessible as other continents, being able to vacation on the moon as easily as in Venice. And conventional chemical fuels just aren't energy dense enough for that, and nor is there any guarantee we'd ever get a working compact nuclear rocket, fission or fusion powered. So what are your alternatives? The space elevator is obviously one of them. You probably know at least the basics of space elevators already. One long, super strong tether running from the equator up to geosynchronous orbit, where it hovers stationary relative to the planet below. Or, if your materials can handle it, several tethers running from places other than the equator up to a shared orbital station, the same as guy wires on radio masts. Your material needs to be a bit tougher, but you could then place one in New York, Paris, and Buenos Aires, for instance, all meet at the central terminal up at geosync. Incidentally, our animation here, the torus, the donut, would represent a rotating habitat providing artificial gravity. We'll be talking about those a lot in the future, and the sphere is simply a counterweight or anchor. Now, finding a material strong enough to hold its own weight for tens of thousands of miles of length is easier said than done. Every material has what's called a breaking length, or how long something can be in Earth's gravity before it breaks under its own weight. And for most materials, like rope or steel, this is on an order of about a mile, or 10 or 20 miles, or even stuff like Kevlar, which is only about a little over 100 miles. We need 10 or 20,000 miles for a space elevator. And while you can extend that a bit by tapering your cable to be wider at the top than at the bottom, and gravity does get weaker as you get further away from Earth, the simple reality is we really don't have anything strong enough to build an Earth space elevator yet. It should be noted that even if we can't do one on Earth, that doesn't rule them out for other places. Your tether length depends on the world's day length and gravity, and how long they can be without breaking depends on the local gravity. You can do one on Mars that's shorter and made of weaker material, or on the moon that's actually longer, but could be made of regular old steel or aluminum because gravity is so weak there. Now, space elevators would definitely be handy, but there's no guarantee we'll ever find a material strong enough and cheap enough to build them with. So are we screwed then, if we never find a better basic rocket or stronger material? Well, no. We still have a few other options, and one of those is called an orbital ring. In some ways, this is actually a better option than a space elevator, too. They don't get as much coverage in the press or in science fiction, so we'll talk about them in a little bit more detail. An orbital ring is a giant ring around the planet, which might be only a few feet wide or dozens of miles wide, but around the entire planet. Unlike a space elevator whose tether is tens of thousands of miles long and straight up, these are tens of thousands of miles long and wrapped around the planet instead. They hover a few hundred miles off the ground and do not move relative to the ground below it. In our animation, they're not really to scale. One can build one of these things, in theory, of any size, but the first one up would probably be so thin you need a telescope to see it. Once in place, you'd be able to lift up matter into space at energy costs far beneath what we spend moving objects by normal air freight, let alone the cost for getting things in orbit. Now, how does such a thing work? There's a couple ways to do one. The simplest and original design is to take a long circular wire up into orbit, giving off a magnetic field, spin it up to orbital speeds, and magnetically levitate objects over the wire that don't move out to the ground below. The wire spins under them and they float in place. You can stick a second one up in parallel, add floating structures called ring stations, slap on solar panels to keep the power running, and drop a tether down to be used as an elevator, one that doesn't require anything like the strength of a normal space elevator. You could also do this by building it as a big pipe surrounded with superconducting magnets, like a giant particle accelerator, and just run mass through it, similar to a magnetic railgun or, again, a particle accelerator. We often call this active or dynamic support, and we'll see this idea a lot in future videos. But it's fundamentally a lot like hooking up both ends of a garden hose to a pump. It will spring into a circle and resist pushing or pulling on it once you turn the pump on. Once you have a small one in place, you drop some tethers and haul up more construction material, and you could do another one higher too, since it can be at any altitude. You can then build a sheath around the entire thing, an orbital ribbon if you prefer. You can keep adding more parallel rings or other rings at different angles. Orbital rings don't have to be around the equator. Once one is up, you can just keep adding more and more very cheaply, and you can supply power to the magnets by solar panels. Can we build one of these? Yes, they are entirely inside known scientific laws. So, why haven't we? Well, for the same reason we don't have a moon base. We can do it, but it would be very, very expensive. When Nikola Tesla first suggested this idea not long after the American Civil War, we obviously were in no position to even seriously contemplate building one, and it got shelved for nearly an entire century. Arthur C. Clarke of 2001 Space Odyssey fame and Paul Birch, a scientist who will get mentioned in these videos a lot, both played with the idea again in the late 70s and 80s, but Birch calculated that getting one up into space would cost several $1 trillion. This could be done for a lot less if the materials could be sourced from off-world, like the moon. But, since the whole point is to make it cheaper to get stuff into space, it has a flavor of being a catch-22. It isn't quite, though, because being able to ship people into space by the million isn't the same as setting up gigantic robot factories that built themselves, so one might be able to build those factories with the robots, then build the rings so you can ship people up to them in large quantities. We want to be able to put large quantities of people in space who started on Earth, not just run robots or send a few people up who breed more people up there. That doesn't mean we can't go the robot route first to set the stage. The cost estimate was also circa 1980. I haven't seen a more recent one, and since then we've made some major improvements in materials, magnetics, and rocketry, which would likely make it a lot cheaper. And since you can use these for hypersonic travel around the planet, not just off-planet, it comes with a more direct and near-term economic advantage. Plus, as huge as several $1 trillion to build one sounds, that's almost all launch costs for initial construction. Expanding a ring and building a second one would be massively cheaper. It's a one-time buy sort of item, and so it isn't off the radar. But understandably, nobody wants to be looking at making something like this until we spent many decades checking if other avenues might be available. It's the sort of thing you would build when you're fully committed to doing off-world industry and colonization, not just some scientific research like we do now. With one in place, you can move freight into space for energy costs comparable to interstate shipping. They are very like space elevators in that respect, but don't require any super strong materials that we may not ever be able to mass produce. So, that's orbital rings, our first look into megastructures in space. If you want to be informed of future episodes, hit the